Hello everybody and welcome to your review for Unit 7. In this video, I'm just going to be going over like the quick highlights from the main learning targets that are going to be emphasized on your Unit 7 test. It's not going to be comprehensive. If you need more review on any of the specifics, you should go back and rewatch any of the AP Daily videos. You should look at your chill. And you should look at the I do, you do, we do resources. There's a lot there. But like I said, this is mainly meant to be just like a quick overview of like the topics that are going to be a focus on the Unit 7 test. But yeah, it's not like there might be a couple questions on some things that are not in this video. But with that said, let's get started. So just a quick reminder on the main things on dynamic equilibrium. Remember, equilibrium means that both the forward and reverse reactions are happening simultaneously. You could have different starting conditions. So like in this one, we can see that we started with HI and that decreases over time, H2 and I2, then that decreases over time. Whereas the HI starts at 0 and that increases over time, the concentration of it does. And once the concentrations are no longer changing, that's when we have reached a dynamic equilibrium. It doesn't mean that there's no more reaction happening. It just means that there's no observable reactions happening. And we could start in the reverse situation where we have HI, in this case it ends up being a product, where we have a lot of product and no reactant, and then the product decreases and the reactants increase, and then they reach a dynamic equilibrium at the same point. Dynamic equilibrium means that nothing is changing anymore. So this is a review of one thing that we looked at before where we got, let me move myself to the right hand side. There we go. We got SO2 and O2, and we can see here that dynamic equilibrium is reached once we get to point or time C here. And we have one species that's decreasing and two species that are increasing. So we know that these bottom ones are my reactants and this top one is my product. So just a quick review on like the graphical representation on like what is equilibrium actually. Again, just a quick overview of what that stuff is. Okay, one of the really big things that you need to know is how to calculate the equilibrium constant, or K. And remember that it's a ratio of products to reactants, all raised to their respective coefficients at equilibrium only. And it's always going to be products divided by reactants. And you can see that there's two different versions of this equation. They are calculated in the same way, but their notations are different. So keep in mind that the one on the bottom is for pressure of gases, and the one on the top is for concentrations of things, or molarity. And you do have to use them appropriately. Like if it asks you to find Kp, you gotta write out the expression at the bottom, otherwise you may lose a point on like say an FRQ or something. And yeah, there we go. So then when writing your equilibrium constant K, remember we only use aqueous or gas phases. You do not include solids or pure liquids, generally speaking. Because those things do not change the rate of the reaction. Because remember that the equilibrium constant is based off of rate laws. And then to also connect this with rate laws, the equilibrium constant, capital K, has no units, which is nice. You don't have to calculate those because they just don't exist. Then when we're talking about the size of your equilibrium constant K, remember that if K is greater than 1, that means that the reaction favors products, meaning that the products are dominant at equilibrium. And we'd say that the equilibrium lies to the right. And if K is less than 1, that means that the reaction favors reactants. The reactants are dominant at equilibrium, and we'd say that the equilibrium lies to the left. And one other thing worth noting is that if K is greater than 1, meaning much bigger than 1, like times 10, it's like 6 times 10 to the 10th or something like that. A really big value. That means that the reaction says favors. That's not what I meant to say. It means that the reaction goes basically to completion, meaning that there are no, basically no reactants in this, and that basically then is no longer an equilibrium problem, and it's now a stoichiometry problem. Reaction quotient Q, it is not if your problem does not explicitly tell you that your system is in equilibrium, then that means that we can't assume that it's in equilibrium. You must assume nothing. We do not know whether or not it's at equilibrium, so you're going to want to calculate K. Sorry, you're going to want to calculate Q, and the Q expression is the same as the K expression. And then, so what you can do is to calculate Q, compare it to K, and then that tells you if you're actually at equilibrium or not. Q is the situation for when you're not at equilibrium. So if K and Q are not equal, then you're not at equilibrium. If K and Q are equal, then you are at equilibrium. So you have to compare K and Q a lot, remember. So when comparing them, if K is less than Q, you need less products and more reactants, so proceed to reactants. And you can see this like in this diagram here where I've got lots of products, not enough reactants. So then I have to proceed to the left, meaning that I need to make more reactants to make sure that my K and Q are equal. So too many products when compared to equilibrium, so your numerator needs to decrease, so products need to decrease, and the denominator needs to increase, where that means I need more reactants. Okay, a lot of different ways of saying the same thing. And then just on the flip side, if K is greater than Q, you need more products and less reactants, so you proceed to make more products. So you can see that graph, or not graphically, but pictorially, I don't know, illustrated by the size of the words here. So I don't have enough products, I have too many reactants, so I need to increase my numerator by making more products, which also decreases my reactants. So then if that happens to the right level, then my K and Q would be equal, then I would be at equilibrium. But currently, as these situations are, they are not at equilibrium for different reasons. One other thing that you need to know is what happens to K and Q when, I don't know why this is all glitchy. Let me try something. I went offline. All right, looks like it's working again. Okay, so let's keep on plugging through here. Get my laser pointer back. So what happens to K and Q when you, so this is not a huge emphasis, but it comes up. So it's something that you need to know. So if you reverse the reaction, you got to inverse, you got to take 1 divided by K. If you multiply the reaction by a factor, n, so let's say you take n times the reaction, what happens to the coefficient or equilibrium constant? You would raise it to the power of whatever you multiply by, so like k to the n for this example. And then combine multiple reactions, you just multiply your k values together. So again, just a quick little blurb about that. Not a huge emphasis. Ice tables are a big emphasis. You will definitely have at least one or both FRQs will involve ice tables. So to recap, if 0 is in the initial row, that's the direction that the reaction proceeds. If you don't have a 0 somewhere, then you have to calculate Q to figure out which direction the reaction is going to proceed. And then there's 2 different ways to do an ice table, or 2 different problem-solving strategies with just a blank ice table. If you need to find an equilibrium constant with an equilibrium constant is given, it's a shorter problem. If you need to find an equilibrium constant without an equilibrium concentration given, that means it's a little bit more involved. That's all I'll say. And then for those 2 longer ones, there's 2 different, really it's 3 different ways of solving it. The 2 main ways, without having to use like the equation solver or like graphing it and finding a root, would be doing the perfect square method, where if you end up with perfect squares on the top and on the bottom, you can just take the square root and it's a lot easier to solve. And then the one that's kind of messy, but it makes sense if you get used to it, is the small change approximation. You can make x equals 0 for the reactant if k is like less than 10 to the negative 3 or 10 to the negative 4. So basically, if you have a small equilibrium constant, you're not going to really proceed to products very much. So you're going to assume that there's going to be a small change, just a really small change. And so then we can assume that we can make an assumption basically and make the math easier. And then there you can use your calculator to do like a quadratic solving, or in whatever way you can do that. So as a refresher, of this. These were problems that we did before together as a class. So here we had this problem. So I can zoom in. There we go. Where we were given the equation and we were given our starting concentrations of CO and H2O, and we wanted to know what the value of the equilibrium constant was. So in the ice table, we fill in the initial concentrations that were given, and we are not given any information about CH3OH, so put in a 0 there. So we know that the reaction is going to proceed to the right, and so we're going to gain X, and again, it's the X or 2X or whatever, 3X is based off of the coefficient in the equation. And so then the C is for change, so then we lose, X, 2X or whatever, and we gain for whichever direction the reaction is proceeding. And then the equilibrium row is just an expression based off of the initial plus or minus the change. So in this case, it was 1 minus 2X. That gave me 1 minus 2X there. And so what I want to find is, so this one told me directly that I had 0.15 molar at equilibrium for CO. So I know that 0.5 right here, 0.5 minus X is going to give me that 0.15. So then I can use that expression to find what X is. Then remember, once you find X, you do not want to stop, generally speaking, when you're doing an ice table. You want to plug that X back in, and then find what we need to find. So in this case, if we want to find the equilibrium constant K, we need to know what the equilibrium concentrations are. So that's why I'm going to plug X into these expressions. And then at the very end, once we have those concentrations, we can use our equilibrium constant expression. And this is based off of the equation, products divided by reactants raised to their powers. Plug in our value, and then we got our equilibrium constant value there. Then the ones that are a little bit longer is when we're not given K and we're not given our equilibrium constants. Sorry, I just repeated myself. We're not given the equilibrium concentrations. That's what I meant to say. So we set it up in the exact same way, and we go through and we set up our expression. So here's my expression. I'm skipping all this stuff in the middle here, but it's set up in the same way as what I had before. And this is the example of the perfect square one. So I ended up with 2x squared over 0.2 minus x squared. So then you can take the square root of both sides, and then it makes the math easier. And once again, we find x, but we don't stop, because what we want to know is what is the equilibrium concentrations. And so I scroll down, and you can see where I plugged in my information here, and we can do some double checking as well. And this was one where we had to compare K and Q, because I was given this equation and I was given concentrations for each of the species, so I2, Cl2, and ICl. So because there's no zeros at the beginning, I don't know which direction the reaction is going to proceed. So what you have to do is you have to calculate Q, and then compare that to K, and that's how you decide, oh, okay, it needs to proceed to the right to make more products because my Q is less than K. Too many products, or not enough. Sorry, Q is less than K, yeah. So not enough products, so proceed to the right. And then everything else is the same. Okay, so really quick recap of ice tables. If you need to go back and rewatch videos, I would highly recommend it, because that's going to be a pretty big emphasis on the FRQ section of your test. Then Le Chatelier is going to be a big emphasis kind of just all across the board. It's a really big idea. So remember that Le Chatelier tells us once you're at equilibrium, different things can stress the system and cause it to shift to the right to make more products, or shift to the left to make more reactants. And so, generally speaking, if you have more reactants are added to the system after it's at equilibrium, it's going to shift to the right to try to reduce that stress. And if you reduce reactants, it's going to shift to the left because you have less reactants. So then it wants to reestablish that ratio of reactants to products. And so if you take away reactants, then that ratio is messed up. So then it has to shift to the left, or shift to make more products. Shift to make more reactants, so that to reestablish that ratio. And just the same for products. If you have more products, that's too many products, so then it's going to shift to the left. And then if you decrease products, it's going to shift to the right or make more products. And that's that. And that's, if you can get at least that much, you've got 90% of what Le Chatelier is all about. The rest of the stuff is just different variations on how you can do different stresses. But if you can come back to this idea of comparing reactants to products, you have the gist of Le Chatelier, okay? So if I change the temperature, that's like doing a shift of reactants versus products if you treat energy as a reactant or a product. So you want to treat energy as a product if it's an exothermic reaction, and treat energy as a reactant if it's endothermic. And if you do it that way and literally write it into the formula to help you with this, then it can be temperature can be treated the same as above. So if I have an endothermic reaction and I decrease the temperature, then it's going to have a shift to the left, and vice versa. And you can think of all the different combinations that we can have there. Then if you have something that is a gas, if you increase pressure, which is the same as decreasing the volume, right? It's going to shift to where there's more particles. So you can determine that based off of the balanced formula. If I have A, arrow, B plus C, I've got 2 moles of gas particles on the product side and only 1 mole of gas particles on the reactant side. So it's going to shift to where there's less particles, so it would shift to the left and create less particles. And then the vice versa is true. So if I have a decrease in pressure or an increase in volume, same thing, right? It's going to shift to the greater number of particles. So same idea. You're going to look at the balanced equation and count how many moles are on the left or on the right. And remember, if something has a coefficient, then that is more moles, right? And then a catalyst does not create a shift. It just gets you to equilibrium faster because it speeds up the forward and reverse directions of the reaction equally. Okay. You with me still? Okay. Okay, solubility equilibria. That one's another really, really big one. You're gonna see that emphasized to a fair degree on the test. Not as much as Le Chatelier, but more than other learning targets. So, for solubility equilibria, remember KSP is just the specific case of the equilibrium constant for a slightly soluble salt. If a salt is perfectly soluble, then we're not dealing with equilibrium. Like in the bottom right hand here, NaCl is completely soluble because it's one of the snap ions. One of the ions that are always soluble is sodium. And so that will proceed to completion. That will have a really high K value, like times 10 to the 15th power or something. So that's not an equilibrium situation. We deal with them when we have a really small K value. SP is just for solubility product. And then we have some always situations for these. We're always going to base our expression as if the solid salt is going to its aqueous ion. So we've got lead chloride going to the lead ion and chloride ions. So then we're never going to have anything in the denominator because we're always going to have a solid as a reactant and aqueous species as products. So you're always going to have a KSP expression where you have 2 things multiplied, maybe raised to a power if it has a coefficient. And you get that coefficient based off of the subscript from the solid part. And then remember that bigger K's equal more products, and smaller is less products. So the products are always aqueous and the reactants are always solid for KSP. And so if you have a higher K value, that means it's more easily dissolved. It's more soluble. If it has a small K value, like 10 to the negative 14, it's going to be less soluble, generally speaking. So let me go here. So let me use this example that we went over in class. So I have XBr3 that has a KSP value of 4.52 times 10 to the negative 8th. So not super soluble, probably, but let's say instead of it asking what the concentration of these ions were, let's say it asked for the solubility of XBr3. If you are finding the solubility, all that you're trying to figure out is what S is. Notice how this is an ice table, but instead of putting X's in, I put in S's. That's to remind us that S is just the solubility of this solid, okay? Yeah, if you find S, you find the solubility. You do not have to do an ice table for these, but it's not a bad idea. The reason why you wouldn't have to do an ice table is because you can recognize that if this is my balanced equation here, about 3Br and just one of these, then I know that I'm going to end up with a 3S and an S. And that 3S is going to be raised to the third power because that's what my KSP expression would be. So then I would end up with S times 3S cubed. So then I'd end up with KSP equaling 27S cubed. And then I would have just whatever the KSP value is that's given to me in the problem. So if you can skip to that step, great, awesome. I'm so proud of you. But a lot of you will probably want to do the ice tables as that safety net of making sure that you're setting this up properly, because it's very easy to forget that the 3 is also cubed, or forgetting just 3 in general, or forgetting to cube it. So it's not a bad idea to set up your ice table for your solubility expressions to help you understand what's actually going on here. Keep in mind that you can only compare KSP values if you have something that has the same ratio of anions to cations, meaning that if I had, let's say, PbCl2, so I had that one earlier in the presentation. If I had PbCl2, I could not compare that KSP value to this KSP because PbCl2, that's a 1-to-2 ratio, and this one is a 1-to-3 ratio. So I cannot compare these. This is like comparing apples and oranges. However, if I had, let's say, aluminum chloride, so AlCl3, and I wanted to compare the KSP value to this one, I could, because it has the same ratio. AlCl3, that's a 1-to-3 ratio. So then this one also has a 1-to-3 ratio. When in doubt, compare S's. S's will tell you the molar solubilities much better than just comparing KSPs. Let's see here. So what else do you need to know here? So this one says calculate the molar solubility. So note that we went through here and we just wanted S. So you do your ice table. And then if you have a common ion, like in this case, where this one says that it's dissolved in 0.2 molar calcium nitrate. Nitrate is one of the snap ions, so it's going to completely dissolve. So we know that the molarity of this is the molarity of Ca. If this said Ca2, then we multiply it by 2. But anyway, so I would put in that 0.2 here. We know this is going to proceed to the right. We go through all the ice table steps. We calculate what S is, and then that's how we solve this. Okay, so common ions and acids, bases. Mainly the thing that you need to know conceptually is that if I add a common ion to this, then we have to think about Le Chatelier. So if I add some OH to this, so I've got zinc hydroxide, and it's got a very small K value, so it's not going to produce very many products. But if I add in more OH in some way, so let's say I add in some sodium hydroxide, I'm going to have more OH, so this needs to shift to the left, meaning that I'm going to create more solid, meaning that it's going to be less soluble. I'm going to have more precipitate in this situation because I've added OH. Now if I add an acid to this, let's say I add in some HCl, that the H ions, the H plus ions that are floating around, those are going to react with the OH to neutralize, to create more water. So basically what I'm doing is I'm taking out OH in that situation. So if I add an acidic species like HCl, I'm going to cause a shift to the right, meaning I'm going to create more aqueous species, less solid species, meaning that I'm going to have a more soluble environment for zinc hydroxide. I'm going to proceed to the right. Okay. That was a quick review of everything. I'm going to make a second video that goes over some practice problems related to each of these things. some multiple choice questions, and some FRQs, so make sure you check that out. Otherwise, you can check out the slides. The slides are going to have the same exact stuff that's going to be in the video. The main difference is that in the video, I will talk through a lot of the stuff rather than you just kind of reading through it. All right, thanks for watching, everybody, and be awesome.